far back? Why doesn't everyone move up?
I'll warm you up here.
I just can't.
Always keep my computer, no matter what.
Okay, so we're gonna get started. I'll ask everyone to move up. It's like we have no mic, right? So it's gonna be hard to.
Yeah, we have no mic, so if you want to move up, feel free. Otherwise, you'll have to talk loud.
I can do that.
So welcome. We're going to be going through a couple things today. Doug's going to cover web animations, and then we've got a session on Meteor. We're doing some announcements, a couple breaks, so you'll have another opportunity to get pizza and a drink. I guess, this is, I think, our 6th month doing this meetup, so it's been growing nicely. We're looking for feedback. We want to know what you'd find helpful as far as content, so we can start passing those ideas around. So far, we've done a lot of overviews of different libraries. Perhaps we want to see more specific techniques. We're looking for ideas, what topics we can pass around. And again, if you have something to share that you think the group could use, we're definitely interested in other people presenting. So, Doug, why don't you get started with web animations?
Thanks, Mary. Okay, so I'm going to be talking about web animations and transitions, and I'm actually going to be doing something a little bit different this time because I think that in the past, a lot of the talks have been focused on how to use a library, how to understand that library, that kind of thing. But what I think we're kind of missing is an actual understanding of what's going on under the hood of some things. So in this case, what I'm going to be talking about is more the back end of the graphics engine and how browsers actually render animations and transitions. And you might be wondering why I think this is actually useful. And that's because there's a lot of gotchas to animations and transitions. So a lot of things won't be quite as performant as you think they will. So when you actually go to run them, they're really slow when you don't expect them to be. So without a solid understanding, fundamental knowledge of what's going on, you won't know what's happening and you won't know how to fix it. So my goal here basically is to give you that understanding so you know when things are slow and why they're slow, and then what you can do about that. So my name's Doug Shirk. I did the AngularJS talk here before, and now I'm returning for this talk. You can find a presentation at this bit.ly link. It's a Google presentation. Anyone can view it. You can comment on it if you want. Also, if you have any questions along the way, just feel free to stop me at any point. I want to try to keep this like a conversation, so any questions are fair game. So please ask me if you have anything. All right, so let's get started. So just a quick overview. So as I said, this is going to focus mostly on the back end and how browsers render these things. So you might be wondering what's the difference between animations and transitions. So an animation is basically something that can have intermediate states. So when we animate web content from one point to another, we can have states such as if we're animating a box, we might have a box here, and then it goes up here, and then down here, and then up here. And that would be an animation, because we have intermediate states that are not just going from one point to another. On the other hand, though, transitions are designed to go from one spot to another. And I'm going to go into more detail on this later and how we actually use these things. So just a little bit about my background. So I'm a former engineer at Mozilla. I built Firefox OS's panning and zooming implementation. And this is deeply intertwined with animations and transitions code. So that's why I have an understanding of these things. And because of this, I have some stories from the trenches about this kind of stuff, and the sort of performance bottlenecks we run into when building it, and stuff like that. Okay, so I was talking about animations, and I gave you that example of the thing bouncing around. So this is a more specific example. What we have is called keyframes, and these define certain intermediate states that we should target, depending on the animation. So in this case, we have a medium-sized circle start at the beginning. That's going to be our first keyframe. Then we go to a smaller circle. And in the meantime, between these two states, the browser is going to interpolate between those. So as it's transitioning between the start and the keyframe 1, it's going to be gradually shrinking the circle and moving it to the right and up. When we get to the next keyframe, keyframe 2, we're going to be expanding the circle slowly until it gets to keyframe 2, and then we'll continue interpolating onward until we get to the very end. And these things will all happen at a defined rate. For example, we might say that the animation applies over a course of 5 seconds. So in that case, keyframe 1 will probably happen around 1.5 seconds in, keyframe 2 will be 3 seconds, etc., roughly. Okay, so here's an example of animations. So here we have a red rectangular div. It's going to start at the top of the screen. It's 100 pixels wide and tall. And we're going to be applying a keyframe-based animation. And here we have the way to define keyframes. So we use the @keyframes keyword along with the name of the keyframe collection. And we have 4 keyframes in this case. That's 0%, 25%, 75%, and 100%. The percentages are the number along the timeline. So in this case, 5 seconds. So 25% would be about 1.25 seconds into it. And at each of these points, we define a different top, which means that blocks will transition up and down based on these top parameters. So we start with 0 pixels, and then about 1.25 seconds in, we're going to go to top 200 pixels, which moves it down greatly to the bottom of the screen, at least within regards of the size that we have here. Then at the 75% point, we're going to have top 50 pixels. Remember, it's interpolating in between these. So for example, we said that 25% is going to be about 1.25 seconds in. But halfway between there, so like 0.6 seconds, it's going to be about 100 pixels, because we're interpolating as we're going through it. So I'm going to actually run this now and show you what it looks like. So this is just a YouTube video. I could also run it as a actual demo, but this to be sure, question?
So, does the infinite thing mean that it just keeps...
Yeah, good question. So in the video that I just showed, I stopped at a certain point, but if you actually ran this in your browser, then it would keep going over and over. And that's because of the infinite keyword.
So because of infinite, would it like jump from 100 pixels to 0 pixels at the start of the next cycle?
Yeah, it jumps back, yeah. So basically, you're responsible for defining another keyframe that would take it back to the start position if you want that to be smooth. Any more questions? Okay. Okay, and now we have a transition example. So now that you understand keyframes, the understanding of transitions is actually really simple. You can understand a transition as being going from basically one keyframe to another, and you have no option of having keyframes in between. So in this case, we still have the same box, but instead of animating the position of it, we're going to be animating the width and height of it. So basically, we're going to double the width and height of it. Here we have the transition keyword, and we define width in 2 seconds and height in 2 seconds. And what that means is that whenever we modify the width or height, within 2 seconds, it should go to the new property. So we're starting at 100 pixels for each, and we're going to 200 pixels. So let's see how that looks. Okay. Is there a question? Okay, so now you might be wondering, go for it.
Sort of, like, it's one of those things like, so on hover, it does this, and so like, if you were to hover off of it, then what happens to the transition at that point?
Oh, so what would happen is the property that you applied before that, assuming that the new property.
Can you repeat the question so people at the back?
Sure, yeah. So the question was, what happens when I hover off of that element if the selector I'm using is hover to apply the transition? So the answer is that the transition property itself, the thing that defines that we should go from one state to another smoothly, is on the element itself. It's not on the hover keyword. So what happens when we hover over it is that it applies a 200 pixel height and width. And then when we lift off our cursor, then it's going to go back to 100 pixels slowly. So it'll be like a slow transition because it still has the animation property on it, or rather transition property on it. But on the other hand, if the transition property was applied on hover, then in that case it would just snap back.
I get it.
Okay. All right, so you might be wondering how graphics cards are actually relevant here. And here I'm going to give you a good analogy for understanding this. So the way I like to think about it is a CPU is kind of like having a small team of bodybuilders that do things for you, like carry stuff around. They're really, really strong, but you only have a few of them. And in most computers, you're going to have somewhere between 2 to 8 cores. So it's like having 2 to 8 bodybuilders. On the other hand, though, a GPU is like a massive team of Oompa Loompas. So it's like having like 1,600 Oompa Loompas in the case of a Radeon HD 5870. So each of them on their own is really, really weak, but as a team they can do a lot of things that are very easily distributed. And another key thing about this is that the Oompa Loompas are very, very far away. So whenever we want to give them any orders, it's a really expensive operation. And also, the bodybuilders are the ones that, or rather the CPU is the one to direct the GPU. So whenever we have any operations going to the GPU, it must first go through the CPU first. But the CPU is not actually evaluating those. All right, so now let's use cases of the GPU based on this like kind of shallow understanding. So the cases that you want to use the GPU are things that can be easily parallelized. You might also want to do it for high bandwidth operations. For example, copying a texture back and forth. Another thing is that things that require very little direction. So if you can batch operations together and send them all as one to the GPU, that's ideal. And I'm going to go through an example of that. So this example is how you would not use the GPU. What we're doing here is just some simple mathematical operations that do not require going back and forth. because they can be batched up all as one. But in this case, we are. This is like how you should not use it. So we're saying arbitrarily, let's say x equals 3, and now we're going to ask the GPU, okay, what's x plus 1? The GPU says 4. How does the CPU that? The CPU says, okay, let's store that into y. And then the CPU asks the GPU, okay, what's y divided by 2? That's 2. Comes back to the CPU finally, and now the CPU says, okay, now with that information that we have, we draw 2. So the problem with this is that we're going back and forth unnecessarily. So how we should do this instead, and remember, each of these operations going back and forth is very expensive. That's where the bottleneck is. So how we should do this instead is we can batch the entire operation up into one single operation. Or sorry, we can batch up the entire expression into one operation, and then send that entirely on its own to the GPU. And the GPU is responsible for doing this all on its own. So we still have one expensive operation where we're telling the GPU to do these things, but because the GPU is better at this kind of stuff, it doesn't matter because it's still faster than if we calculated it on the CPU. And this applies to any sort of graphic concepts. So like copying textures, drawing a scene in a game, like anything like that. All right, so now some terminology. And by the way, this is all actually going to be relevant to animations and transitions. Without this understanding, you're not going to be able to follow why things will be slow in the future. So first of all, painting. So painting is drawing pixels onto a buffer, usually from scratch. And this is actually very analogous to how like an artist would paint on a canvas. Like it takes a long time, it's drawing something from scratch, and it's using like a canvas, which in this case is our buffer. And you can think of those two analogously as well. Next we have a buffer, which as I just talked about is like the canvas for the painter. And it's a block of memory that stores a texture. And a texture is just anything that you're going to see on the screen, basically. So for example, it could be like a wall cap picture you find online, or it could just be like whatever is on your screen right now, rendered by whatever game you're playing, or like your web browser or anything like that. Next, we have the concept of compositing, which is just flattening a series of buffers so that they're visible. I'm going to go over an example of this so you can understand this better. So let's just hold off on that for now. Next, we have blitting, which is copying a composited buffer onto the screen so that the user can actually see it. And the reason this is kind of different from just painting is because painting is typically done off-screen, or in an off-screen buffer. But then we actually have to show this stuff eventually to the user, and that is the process of blitting. And finally, a concept that isn't actually related to graphics, it's related to layout, is reflow, which is calculating where things should go on the screen based on how web content has defined itself. So, for example, when you make like a grid in your web template, the browser has to calculate where each column in that grid goes. And that's an example of this. All right, so now as I said, I was going to talk about compositing. So compositing is actually very cheap. It's, as I said, very analogous to a painter painting a painting. And then, like, that process is expensive. But then putting it on a wall once it's painted is really, really cheap. It's not difficult to do that. That's basically what compositing is doing. It's taking already painted buffers, in this case our paintings, and arranging them in some useful way. So your window manager is an example of this. If you ever see, for example, your browser on top of like some other window, like Word, for example, that's an example of compositing. Because we're taking one painted buffer, which is your browser, and we're compositing on top of whatever the background is and whatever the Word document contains. All right, so you might be asking now, when do we paint? And the answer is, in games, we're painting all the time. Like, we're not really concerned with that here. And the reason we're painting in games all the time is because every frame of a game is so different that it's basically impossible to reuse anything that we already have. On the other hand, though, in web browsers, we only repaint when something has actually changed. And there's actually cases where we don't repaint anyways, because something like we can go without doing that, basically. And I'll explain more why in the future. Right, so when we need to repaint something, we mark it as invalidated. And we can trick the renderer into not invalidating content, which is basically the thrust of doing animations and transitions. Because remember, painting is very expensive. So why is invalidation bad? For starters, it's not actually always bad. When something changes, we sometimes just have to repaint it, and there's nothing we can do about that. That's a good thing. But the reason it's bad when we're doing animations and transitions is because it forces us to repaint and then composite it instead of just compositing alone. And remember, painting is a very expensive operation. And often, if we're invalidating things, we sometimes have to reflow them as well. And reflowing is a very expensive operation, but that's more of a bottleneck for the CPU and not the GPU. Any questions so far? Cool, okay. So now let's talk about hardware acceleration, which is where transitions come in. So hardware acceleration is basically, in this context at least, using the GPU instead of, using the GPU instead of the CPU wherever possible. So there's other contexts of hardware acceleration. For example, you have sound cards that can do hardware accelerated sound, but like we're not concerned with that here. So the point of hardware acceleration is that we can make things much, much smoother, but only if it's used correctly. So the key to hardware accelerating things and actually having it be faster than doing these things in software, and by software I mean doing them on the CPU, is that we have to avoid invalidation whenever possible. As long as we're not invalidating things that we don't need to be, then we'll have the benefits of hardware acceleration. So here are the properties in CSS that you can use that do not trigger reflow and do not trigger invalidation. So there's 4 of them. Well, there's actually one because it's just transform and opacity. But within transform, we have translate, scale, and rotate. And opacity is just like how much you can see it. So like it might be partially transparent if you set opacity 0.5, for example. And additionally, you might have to apply translate Z or translate 3D, as we can see here. But we can talk more about that later. So basically, these 4 are safe and do not trigger reflow or invalidation when you use them. And that's the important thing, because other properties do trigger these things. So, go for it.
Can you just go back to the previous slide?
Sure.
That note about translate 3D and translate 3D, like, is that meant as like what the browser has to kind of force the GPU, or
I'm sorry?
is that meant as like a browser has to force the GPU rendering, or?
So you can't. So actually, I'm going to talk more about that later. But the case, are you asking specifically about translate C or 3D or what?
Either one.
Yeah. So if you just use translate, then sometimes it won't actually hardware accelerate it. Like it tries to apply some clever hacks on it.
Right.
Like it does heuristic analysis basically on it to figure out whether or not it should. But if you use translate 3D, then you're guaranteed to get hardware acceleration if it's possible.
Right.
But some systems, that kind of stuff is blacklisted. So in the case of like Linux and OS X, you're going to be using OpenGL layers. And in the case of Windows, you're going to be using direct 3D layers. But sometimes those things are blacklisted because the drive that the person is using is so out of date or like it's completely busted that we don't use them. And because of that, we just do everything in software. But if hardware acceleration is possible, if you use translate Z or translate 3D, you are guaranteed to get hardware acceleration for that element. Okay. Any other questions? All right. So there's 3 main methods of animating properties in web content. So the first is using jQuery or JS. So the example of this is using jQuery's .animate function. Next we have animating most CSS properties. So for example, left, width, and color. Actually, you can't animate color. I don't know why I wrote that. But you can animate left, and width. So I showed an example of that before where we took the box that was 100 pixels by 100 and then animated it to 200 by 200. And then finally, so these 2 properties, or these 2 methods require repainting on every frame. Whereas the next method, which I just talked about, was using 2D and 3D transforms and opacity. And in that case, we only have the composite. We don't have to worry about repainting. So of note, actually, I'm going to explain how the .animate function works, so you can understand a bit better why it's so slow. So basically what happens is, let's say we have a box over here, and we want to animate it over here, and we decide that we're going to use the jQuery.animate function. What it does is it starts here, it says, okay, my left is 0. So I guess this would be white for you guys. But my left is 0. And then in the next frame, I'm going to do a set timeout with like 1 millisecond or something like that. And in the next frame, I'm going to set left is 1 pixel. And then I'm going to do another set timeout and say left 2 pixel. And I'm going to keep doing that over and over until it gets where it should be. Now remember the Oompa Loompa example. They're really, really far away. So every time we have to tell them to do something, it's going to be really expensive. That's why the jQuery method is so slow. And I'm going to show you an example of this and why it is so slow. So here's an example I built based on these 3 strategies. The first is using jQuery. The second is using software CSS, so like animating width and height. And the third is using hardware acceleration. And there's a link here. If you guys have a mobile phone, I actually really suggest going to this link because you'll learn a lot more about what I'm talking about. And the reason is because you might be wondering why this actually matters. And on desktops and laptops, it really doesn't, because they're so powerful these days that they can probably repaint and be completely fine. But on mobile, we're very constrained with resources. So in that case, we don't want to have to repaint when we don't have to. So this example will highlight that a bit more. I'm going to play the video to show this now. So as you can see, the jQuery one is very, very laggy compared to the others. And that's because of this CPU pipeline thing that I was talking about. On the other hand, the software CSS and hardware CSS look almost exactly the same, unless you actually do it in a browser. I'm going to play it again and watch the software one very closely. you'll see that at the very end it looks slightly more janky than the hardware one. And that's because we're repainting